Okay. So for the work done by the constant force, the formula is F dot S, which you can write as either F into S cos theta. You can think as a product of force and component of displacement in the direction of force, or F cos theta into S. So you simply resolve the force in the direction of displacement and you multiply with the entire displacement, and this is how you get the answer. So whenever it comes to the work done by the constant force, the method is very easy. Just multiply the components. Now, one thing which you find generally very convenient to write is when the force and displacements are parallel, the work is simply the product of the two. And when they are anti-parallel, then it is simply minus of the two. I hope this is clear what I'm saying. So whenever you see force and displacement in the same direction, the theta will be 0, right? Isn't
Yes,
it?
sir.
And for theta 0, the answer will be Fs. And when they are opposite of each other, theta is pi. And we know cos pi is -1. So it's good to remember that these are the work definition. You can write directly plus Fs or minus Fs. I hope this will be easy to remember. Okay.
Yes.
What we'll do is we'll just write a theorem for the sake of writing. In the last lecture, what we discussed that a block or a mass, which is a rigid body, which cannot be deformed, can carry energy only in one form, and that form is called kinetic energy. So any non-deformable object, the object which cannot be deformed. So generally, while solving numerical, we believe that the blocks are non-deformable. Yeah, we are not going to deform their size or shape. So these kind of objects can carry energy only in one form, and that is called the kinetic form. So the energy exhibited by the block or particles in our discussion will be purely kinetic. Okay. Now in this chapter, because we are going to study the particle dynamics, though, so the kinetic energy will have only one form, which we call translational kinetic energy, or simply kinetic energy, which you know as half mv square. But as you move towards a chapter called rotational dynamics in a near future, then the kinetic energy will have two parts. One is called the translational and other is called rotational. So the spinning object will have a different kinetic energy, and translating object will have a different kinetic energy, and therefore we have two different names. So the names are kinetic, translational, and rotational. And if you go to another chapter called thermodynamics, in which we have the crystal object, crystalline substance, and if you go to the microscopic description of crystals in a chapter called solid state, you will come across, or in a chapter called thermodynamics, there the kinetic energy will have a three separate category. One is called translational, other is called rotational, and other is called vibrational. So vibrational is the energy associated with the crystals. The rest two are associated with gases or liquids, both. And vibrational is one unique property of a solid object, but vibration can be also for any gaseous molecule also, or any liquid molecule also. So as you move in the next few chapters, the complexity of kinetic will keep on growing, but do not worry. Presently, our complexity is going to be very simple, and we simply called kinetic energy. But The kinetic energy, what we are going to call here, by default will represent the translational. So I wanted to make you just aware of this fact that what we call kinetic is one particular name actually, but just to keep the simplicity in check, not to make things complex at this stage, we do not call by the actual name, and the actual name is called translational kinetic energy. Okay, so I'll just introduce a theorem called work energy theorem, because we need to know to solve certain numerical as of now. So in this concept of work energy theorem, we just need to remember certain things. So according to this theorem, total work done on a system. So system may contain one mass or a collection of masses is always equals to total change in its kinetic energy, or you can say total change in kinetic energy of system. So just for your awareness, kinetic energy will have three different forms. Translatory or translational, I would say translational KE, rotational KE, and vibrational KE. And they have a formula. And of course, here we don't have a formula per se, but we have something which we're discussing from now. In particle dynamics, since size of object is not taken into consideration, therefore KE is always KE translational, and we simply write as half mv square. So the V actually represents the velocity of center of mass, but for present discussion, it is the velocity of the body, because we are talking about only translatory motion. Okay.
Yes.
So this is your work done theorem. Okay. So work done by all forces equals to change in kinetic energy. Okay. So there is a simple proof of work energy theorem. So from Newton's second law, so the net force we write as mass into acceleration. Of course, this is the consequence of second law, not second law. So for particle, we know F net equals to mass into acceleration. And the axis will prove for one dimension, but it is going to be true for all dimensions. So the acceleration we can write as V d by ds from the definition in kinematics. So we are going to prove in one dimensions, and therefore we can write net force into ds is mdv, and we are taking m as constant, so we can integrate both sides. The LHS is called the work done by net force, which is like all force, and this we can change from u to v. This is m into v square minus u square by 2, which is clearly the change in. This is k final minus k initial. So the proof that work done by all forces delta. Okay. And you can apply it for any number of force, and need not to be just one dimension. It is for all types of dimension, but this is how we bring the proof in an easy fashion. Okay. So now what you need to remember that work is a event, and changing kinetic energy is called manifestation. Like this is how a system will manifest that whether it has received a net energy or not. So the net force means some force may be giving some energy, some force may be taking away the energy. So the kinetic energy will change, like whether you have received net or not. So when you receive a net energy, it will increase, and when you lost a net energy, then it will decrease. Which means if the positive work is greater than the negative work, you will have more energy after some time. And if it is vice versa, you will have less energy. So the delta K may be positive, may be negative, but that's not your concern. You have to write the work done by all force equals to delta K. Now this theorem becomes sometimes really interesting when in a journey, If we start a journey with initial speed 0 or at rest and you end at again rest, and if the block is acted upon by a variety of forces which I'm not showing, so there are forces acting on this block which you don't see. In such case, the work done by all force must add up to 0, right? Because the initial kinetic energy is 0, you can see clearly the funnel is. And because delta K is 0, so in all situation in which you see that you start from rest, you end up at rest, being at rest, then the work done by all force will add up to always 0, which means some force will do positive, some force will do negative work. Is this clear? So based on this, we have done a question, I think in the last lecture also. Let's just repeat the question, same question. So a block starts moving on a two types of surface. So you start from rest. Let's say this length is L1, this is L2. And you eventually end at rest. So you reach the bottom and you have no velocity. And the other part is rough, other by one part is smooth. So for what value of mu, the block will be at rest? So what you will do is you will first draw the free body diagram. So you know the forces are gravity, then normal. So for the smooth surface, we have just two forces, gravity and normal, isn't it?
Yes, sir.
But the moment you climb the rough patch, you will have normal, which is same actually, gravity, and one more force, which is friction force. Okay. So when you go from top to bottom, gravity is working throughout the journey. Normal is not doing anything at all, and friction is acting only for the rough patch. So you're supposed to write the work done by each force till the bottom and add up to 0. Do it. And then remember, these all are constant force. So to write the work done, it's very simple. You have to just write the force times displacement. Done.
Two sides.
So you know the displacement. You're just supposed to write the work of each force. And as I said, either you resolve the force in the direction of displacement and just multiply them, or you resolve the displacement in the direction of constant force and multiply. So it is the matter of convenience, like what you find convenient.
That's
Okay, tell me.
so mu is equal to tan theta into L1 plus L2 by L2.
So this is what you wrote, right?
Yes, sir.
So mu is tan theta into. This is the right answer. Now, if you remember the question that you solved in friction chapter, it was equal length, right? L and L. So if you put the length as equal, it will become 2 tan theta, right? Or if I give you some ratio that the rough patch is sometimes of a smooth patch length, we may express this in terms of a ratio also. So this will become the ratio of the smooth upon rough plus 1. So sometimes they may say, okay, let's say L2 is eta times L1. If so if this is the case, then mu becomes eta plus 1. Sorry, 1 by eta. So tan theta into 1 by eta plus 1, right? So in this case, what we preferred is that we resolve the force in the direction of displacement. And it is well known to us that this is mg sine theta. And in the direction of mg sine theta, you move from the top to bottom, which means you travel this much. And in the direction of displacement, say force of friction, we are moving in the opposite direction. So we have a negative sign. So minus mu mg cos theta is the force value, and then L2 is the displacement. We simply multiplied because these are constant in nature. So we can use the definition of constant work done by constant force. And so we have this answer. I hope this is clear. It is clear, guys? Tell me.
Yes.
So we are going to solve now few questions of laws of motion using energy method. And in these questions, uh, all forces will remain constant throughout the motion. So let's do this question. And this is our typical Atwood machine. So we all have been solving problem of this nature in laws of motion chapter. And now we are going to see that can we use energy method to get the similar answer. So we'll see the process, of obtaining the answer, how one should proceed, how to think. So for the sake of simplicity, let's assume M2 is more than M1 so that we can guess easily which one will go down, which one will go up. So which block will go down?
Sir, M2.
Okay. So how we start solving question in method of energy, that you have to assume that, let's say, M2 has gone down by some variable. So which variable is suitable here? Can you choose Y?
Fine,
If
sir.
M2 descends by Y, M1 will
Ascend by Y.
ascend by same value, yes or no? Tell me, guys. So this is how you start with. You always start with this this kind of diagram that, okay, this will go down, this will go up. Okay. And we have two moving objects, M2 and M1. So we have to draw the ability of each object. So we have to draw the tension and the force of gravity as part of the FBD. And we have to write the work energy theorem for each object separately. Later on, we'll learn something more detailed. But to begin with, because this is the first lecture of solving such questions, we can start with very scratch. So I'll write for M1, applying work energy theorem. Okay. So definitely after falling through certain height, the block will have some velocity, yes or no? Tell me. So can we assume the velocity of M2 as V?
Yes.
And if it is so, then what will be the velocity of M1?
Also V.
Now, this is by the matter of constraint relation that we are having only one variable V, but in situation of complex constraint, you are supposed to assume V1, V2. Am I clear what I'm saying? So here the constraint is simple enough, right? That's why they have same velocity. But should we assume the same value in every case?
No, sir.
So in every other case, you know the relation of constant relation, right? We have done something called constraint relation. So in general, you should assume V1, V2, but right now it's very simple. And then what you are going to write is you're going to write the work energy theorem. Okay. For M1, what is the work done by tension? Because there are only two forces, so we have to write the work done by tension plus work done by gravity equals to delta. Okay, what is the work done by tension? Tell me. Hello, hello, hello. What is the work tension?
So negative M2GY.
No, tension on M1. How tension is acting on M1?
Oh, sorry, M1.
What is the
So
direction of force?
positive.
Hmm.
Oh. One second. So negative M1GY. No?
No, tension. What is the work tension? How much this force will work?
T into Y.
T into Y. Correct. And how much M1G will work? The gravity?
Minus M1G into Y.
And what is that delta K meaning? Final minus initial. So if you release from rest, then initial is 0, final is how much? Half M1 V square. Am I right?
Yes.
Initial is 0. So we always write final minus initial. We don't write a big minus small. We write final minus initial. So sometimes it may be negative, but you are not supposed to worry about it. Is this clear? So similarly, can you guys tell me for the answer for M2? What should I write here? Tell me. Tell me.
Minus TY plus M2GY is equal to half M2V.
And just like you solve the question of log motion, we do not want tension in our picture, so we can just add 1 and 2. That will get rid of T, right? So 1 plus 2 implies what? If I add the two equations, I will get rid of tension, right? So what I'll get? So are you guys sorry. Okay. So now what we have is, you can see clearly you have something called V square. So what is V square? So V square is twice of M2 minus M1 into G upon M1 plus M2 into Y. So you can clearly see the V and Y, we have a function. And V square is function of Y. It could be, no need to write it this way, but to get the acceleration, the only choice is we have to differentiate both sides. So for acceleration, this is the very standard procedure. You have to write the equation, then differentiate with time. Differentiate both sides of equation with respect to time. Okay. So you could have differentiated in the equation 3 itself. So I'll add 3 implies. If you differentiate with time, the masses are constant, G is constant, so we are not going to disturb, but Y we have to write dy by dt. And the RHS will be d by dt of V square. So we write as 2V into d by dt, which is like change, right? And as Y will grow, the rate of growth of Y is nothing but the velocity. So I hope you can understand this is V itself. And this is M1 plus M2 into V into d by dt is called acceleration, right? And this V gets cancelled. So we get A equals to so we have arrived at a juncture at which we can realize that questions of laws of motion are equally solvable in terms of energy thinking. So if you write things in, write things in terms of energy. And if you wish to get the velocity, see, this is even better method to get the velocity directly. So if our goal is to find the velocity, then I will in fact go with the energy method. But if our goal is to find the acceleration, then probably I'll go to the force method, because that is even more convenient. But a variety of situation will come in which you have to actually write the energy method as a simple result of writing the equation. Okay. So in a complex situation, energy is easy method. In a simple situation, force is easy method. Okay. In a complex situation, if you try to laws of motion, it will become more cumbersome, like the way we are looking right now. So this question we could have solved with much ease, but you can see now things are not very convenient. Okay. But the next question will open your eyes that why we learned this method. Before that, I'll solve one more question in which the constraint idea will be used, which you have already studied in laws of motion. Let's see. So we have so I'll keep it simple. So you can see now we have two blocks M1 and M2. And see, the problem is when you are solving question like this, it is difficult to know what to assume first, because everywhere you have to use the constant relation. So first of all, if I assume that M2 has gone down with Y2, what is the ascent of M1? Can you guess first of all? So see, to solve question, you have to start with some assumption only. There's no way out. This is how we start. So we believe that, okay, someone has gone down, someone has gone up, and then we solve. So if M2 has descended by the height Y2, what is the ascent of M1? And you cannot say directly that this is Y, this is also Y. So you have to stick to the constant relation also. What is constant here, if you remember? So what is the constant here? Tell me. How you find the constant? Do you remember, or you have forgotten everything of laws of motion? Constant we write for displacement as well as velocity, right? So what will be the constant here? Tell me. So the way you solve the velocity constant, you can also solve the displacement constant. It's a similar, both are similar. So you can see the tension acting on M1 is 2T actually. So 2T acting upward, so 2T Y1. And for M2, it is acting upward and Y2 is downward, so we can add T Y2. So we write T dot S and we add it to 0. So tension that displacement can always add up to 0, and this will give you the simple relation of Y2 and 1. So Y2 is, and similarly the V2 will be also twice of V1. So this constant will go hand in hand, the velocity and the. And if you release a system from rest, then acceleration will also go with the similar constant relation, but only in this case it is always true because there is no angle involved. So this is not always, but luckily in our case it is going to be true. So to start with, you have to think on this line first. You have to start with the relationship of constant. Okay. And once you understand this relationship, then you can choose variables, okay, to make it easy. So can you guys write the work in exam for each block mass M1 and M2 separately? And in fact, you will realize that there is no need to solve separately. You can always solve directly also. But anyway. So what is the work done by? So write work in some for M1. And try to realize it that what is the procedure. Okay. I know there are so many things coming together for you guys. And since you don't remember the last chapter also, so it is going to be difficult. But anyway, if you can reinforce those in the learning which you studied earlier, you can actually revise laws of motion as well. So tell me how to write the working experiment for M1. So you can draw the ABD. You can draw the ABD mentally and write the laws of motion. Sorry, working theory. So tell me quickly what we should write.
So 2t y1 minus m1 g
2t y1 minus m1
minus
g
m1 g
y1
y1
equals to
half mv1 square
half
minus 0 half
m1
mv1
v1
square
square. That's
m1 v1 square.
and for m2
minus ty2 plus m2g y2 is equal
minus
to
ty2 plus m2 g y2, right?
y2. Yeah, is
Is
equal to half m2 v2 square.
very good. And do you realize something? If you add these two terms, if you add, always you have to just you need to add actually. Then you will get 2t y1 minus t y2, which is exactly this one, right? Do you realize this? Try to realize this. If you add, you will get this much. Correct? And that is always 0. Yeah, tell me, yes or no? Do
Yes,
you
sir.
guys realize? So what you will come to know later on that this way of writing is not at all required. This is just for your understanding. This is the first time you're solving. So we have m2 y2 minus m1 y1 into g half m1 plus m2 into sorry. So half m1 v1 square plus m2. So see this term will be always 0 without any doubt. In fact, later on you will come to know that it is not at all required to write the work done of tension force, because tension is a constraint force. And the role of constraint force, you will come to know that later on that the constraint force cannot give energy. It can only take energy from one object and give it to the other object. It will act as a transmission mechanism. So tension in the rope is actually favoring the energy flow actually within the system. So every constant in our day-to-day life also, the constant will give you the way to transfer things here, the transfer of energy from one part of system to another part of system. So when we talk about the car or bicycle, we have something called chassis. And chassis is basically energy transfer mechanism. So a good design of chassis will transfer energy from the rear wheel to the front wheel effectively. Okay. And it will have a greater repercussion when we talk about the efficiency of, mileage of a car and the longevity of a, design, like how sturdy the design is. So a design is said to be very highly sturdy if it is able to transmit energy with least deformation. I mean, we'll come to know all this in future. So the design of whether car or bicycle or the design of the frame, by looking at the design, you can realize that it is not so sturdy, it is not so effective. And if the energy is not getting transmitted easily, you will see there is so much squeaking sound coming out of a bicycle also. So when you're applying the brake, the chassis is getting compressed and elongated, and it's kind of not doing the thing effectively. So in the name of fancy design, they forget the physics and they do the bad design. So not all designs are good design just because it's looking fancy. Now to solve question, we cannot solve with two variable questions. So we have to convert everything into one variable. So either you convert into y1 and V1 or Y2 and V2. So what we are left with is M2 Y2. Let me write down once again. Into G half M1 so we know Y2 is twice Y1, so I can convert this into Y1. So M2 and Y2 connect is twice Y1. And I'll keep V1 as such, but V2 we have to replace. So V2 is what? Twice V1 square. Okay. And then you can write as this is 2M2 minus M1 into Y1 into G and half common M1 plus 4M2 into V1 square. And now things are easy. So now we differentiate. So 2M2 minus M1 into G differentiation. Dot dot dot. We know what we are trying to write. Dy by dt is M1 plus 4M2 upon 2. So this will become 2V dV1 by dt. And this is Y1, sorry. So this is dy1 by dt and V1 will cancel out because that's the definition. And what we are left with is into G. This 2 will also cancel out this 2. So we'll get is M1 plus 4M2 into A1. So we got A1 equals to understood. It is clear?
Yes, sir.
Okay. So this is how we write the answer. So once you get A1, then A2 will be twice of this value. So no need to solve. So A2 is twice of A1 and then we are done. So as a beginner, this is how you proceed. You write so many things and then as we become expert in writing, so we do things mentally very fast. So we know that Y2 is twice of Y1. So I'll assume Y1 as Y and this will become 2Y. And therefore this will become V. This will become 2V. So I have reduced the variable at 1 go. And then I will write it and will solve. And from the diagram, we can come to know that if I differentiate d by dt will give me basically velocity acceleration of m1. Okay. So this is how things are done on an expert level when we have already realized. But as a beginner, I always say that, okay, rather than me saying that this is the trick, you come to that realization through rigorous practice. And once you realize, then it will stick with you forever. No need to, you're not going to revise again, no need to think again. It will come to you naturally because you have done a lot of hard work in solving such question. So this is one example where we apply the work in a theorem to solve a very simple question. It may appear difficult, but with practice, you can make it easy, really easy by writing less variable. And also one thing, no need to solve it individually. So we write a work energy theorem at one go. So I'll just show you the faster way of solving. And I'm not expecting that you will understand 100%, but maybe when you will become mature mentally, you can call back this method and okay, realize that okay, this is much easier way of solving. And for this chapter, you can see, you go to laws of motion chapter and you simply solve all questions which you have done with laws of motion using energy method, just to practice, because in SC Verma, in this particular chapter, you won't get such question which you are solving right now. So they will not give you question like the laws of motion type of question, because they believe that, okay, you know things. So maybe 1 or 2 questions will be there, but not much. So see how I am going to solve. I know that if M1 will rise, if M1 will rise by Y, M2 will fall by 2Y. I know this exactly. I can see it. Because if the pulley will go up, it will release the rope from both sides, right? And therefore, because the left will not provide any length, so all length will come from the right side. And therefore, M2 has to fall down by 2Y, right? This length and this length will fall, right? Entire length will come down. Do you realize this?
Yes.
So it was easy actually to understand that what is the constant relation. And we also know that as the Y relation goes, if the velocity of the first is V, then this is 2. And when we are solving question of block string pulley system, work done by tension is not at all taken into consideration, provided you write the work energy theorem for the all masses at once. So applying work energy theorem for system. So I'm not writing individually, I'm writing at once. So what I'm writing is, check it out. M1G is going down and displacement is, sorry, M1G is acting down, displacement is upward. So minus M1GY plus M2G 2Y. Are you guys with me till here?
Yes, sir.
Equals to changing kinetic energy, so we have to add energy of both at once. M1 V square, because V1 is V. And for M2 it is, see, with expertise, the same equation we can add in one line and get that. So M2 minus, so 2M2 minus M1, 2M2 minus M1 into G into Y is half M1 plus 4M2 into V square. And we are done because we know how to differentiate. So we simply write dot, and Y dot is V, and V dot is, this becomes 2V dV by dt, which is A. So with practice, you will also realize that the dy dt will be the V actually. So with practice, we do this really fast, almost mentally, but as a beginner, we have to write all this. It's not so easy to realize. And so you got A as. So for demonstration, I have to write this much, but when we solve problem, these steps are done mentally. And we also realize that this A is representing what? So this is dy by dt, which is A1. So this is actually A1. And so A2 will be twice A. So just make it twice and you're done. Okay. Is this clear?
Yes.
Oh. So do we have some other method of solving? Okay. So now I'm going to take a slightly difficult question. to demonstrate that the constant relation can be trickier at times. But I think, you know what I'll do? Before I go to the next question, I want you guys to solve the previous two questions. And in fact, let's solve a fresh question. Okay, I'll just use some question. Let's try to solve this question with energy method. Just to get some hang of the concept. And not like this. Okay. You can create question like this. It is more about the constant, less about the energy, like how you can think of. So find accession of each block using energy method. Like, try this out, everyone. So you can take your time, try to realize things. Don't be in hurry. Give your time, realize it. First, you have to start with the constraint relation. So assumption of the suitable variable will be the first step. And then write the energy relation by displacing in terms of some variable which you can choose. And then you can solve. I hope the question is clear.
Yes.
Go ahead.
So do we consider friction also?
No, there is no friction. All surfaces are smooth. Done, guys? So you have to actually
Yes, sir.
think very hard. Like unless you will not start solving right now, you will always find the same difficulty level at home also. So it's like breaking the ice. You have to solve one question, then it is done. Then you know how to proceed. So you take all the pain of thinking of constraint and all. And you see, you have done half part of it, you have already done in the laws of motion. So I can assume that you remember those things. Shall I? Yes or no?
So I think I got the answer.
Very good. So Sansa, what's your progress in this question? Are you there?
Yes, sir. I'm still trying.
No, what you're trying? Explain to me like what you're trying to do. Why you're getting stuck in the problem? What you're not able to figure it out? What is happening? Tell me. You try to explain your difficulty. I will try to explain the solution. Tell me. Hello, hello. Are you there?
Yes, sir.
Tell me, no. Tell me like why you're not getting answer. Like where you're getting stuck, or
So
what
writing
you
the constraint relation.
consent you don't know.
So I know.
So you don't remember consent, right? So it's a very simple solution. Today you will only study the consent from the laws of motion chapter. You go and watch the video of consent and make sure that you understand completely, really well. So this is your duty for today. See, that is how we study. When we get stuck, we try to resolve the issue. We don't try to, kind of shelve the issue, put it in somewhere, try to avoid, try to escape. So this mindset will never let us grow. You have problem, that's one thing. But do you want to resolve the problem? That's a big question. And if intention is to resolve the big issue, the job is done. Okay. So constant is, you know how to write the constant. If I assume T here, then this will be T, and T, this will become 2T, right? So if I assume this, okay, let's say this goes down with Y, and this goes with, let's say X. So 2Tx minus Ty equals to 0, correct? Which means Y equals to 2X. Is this clear? And therefore Vy equals to 2Vx. I think this is also clear. So let Vx equals to V. So Vy becomes 2V. And then I'll add the working theorem, 2mg, and nothing. So the only work is being done by the, we never write work of tension. So what we write? 2mgy. I'm done. Equals to what? And you can see there is no work done. Do you see any other work? mg will not do any work here. Am I right? And neither the normal. So which force will do the work on a system? Tell me.
Tension.
Tension? The work done on a system. Which force will do the work on a system?
Gravity.
Only the gravity on the hanging mass.
Yes, sir.
And gravity on the horizontal mass, I mean mass on a table will not do any work, because in this direction we are not moving, right? So you need to realize all this. So first step is draw the ABD, and you have to spend time in realizing this part. I mean, you have to really work hard. Think for the entire day, like why it is happening. And when you realize it's easy, piece of cake. So the work done by gravity is 2mgy, and that is the only the work. There is no other work at all. That's so easy, imagine. And then energy, half 2m Vy square and half m. I'm done. So 2mgy and Vy. Okay, what we are assuming? We are assuming Vx equals to V. So why we cannot as 2x? I'll add 2x. I will add in terms of x only. And Vy is 2V. So this is 4V square and half mv square. And why I'm writing in terms of x? Because I'm taking the variable v, okay, for the Vx. That's why. So 4m, okay, I think m will also cancel out. M, M, M. So we have 4gx is 4v square plus v square by 2, which is 9v square by 2, which is, okay, so v square is 8g by 9 xo 2v dv by dt is 8g by 9 dx by dt, and now this will cancel this v. So the accession turns out to be 4g by 9, and this will belong to what? Vx. So this is the accession. So ax is a, and the ay will be 2. Correct? 8g. So these are the answers. So now try to figure it out like what is the actual difficulty you're facing, like in terms of writing, replacing variables. There are many steps involved, right? Okay, what I can say. So constant is something that you can practice. Yeah, Siddhant, you got the same answer?
Yes, sir.
Very good. And the last question, now this is even more challenging. I don't know, should I give or not, but anyway, I'll go away. I mean, go with the question. This is a really challenging problem from IIT 1985. So this question will give you another perspective. This is 1 meter. Then there is a pulley. And then there's a long rope. And then there is a mass. Okay. So let me put this pulley at rest. Okay, so let me read the question for you guys. Where's the question? Okay. This is capital M of mass 2 kg. And this is small m of mass 0.5 kg. And take G as 9.8 meter per second square. If system is released from rest, then find the speed with which block of mass will hit the Wall. Okay, the wall is extended actually. Hmm. So what you can realize that this is a fixed point. This is kind of fixed. So can you guess the path of the capital M motion? How the capital M will move? Any guess? Tell me. How the capital M will move? Any guess?
So these strings can stretch also.
No, these are inextensible. But yeah, the small m can go up as capital M will fall down. So this is a very long. This length is much longer than 1 meter. Imagine the small m will never hit the pulley. Okay. My question is, what will be the path of capital M? First, only understand the path, how it will move.
So vertically downwards.
No, it is attached to string. No? So the tension is always there. The string never becomes loose.
So will it be a curve sort of?
It will be exactly a circular path because the one end is fixed. So if you have anything, a mass, if you suspend at one end, how it will move?
Yes, sir.
It always moves on a circular track actually. So this is the first idea which should click, and generally it is difficult. That's okay. I understand. So this is the first part. Okay. Okay. And you can clearly see that at the moment it is about to hit, the direction of velocity will be exactly like this. Correct? So let's call V2. And by the time you are going here, the block will rise. And what will be the direction of motion of the block? It is going to be upward only. And we will call V1. And not only this rope, this part of the rope, the right side of the rope will actually will come like this. Do you realize this? I don't know.
Yes, sir.
So, okay, don't consider this deviation. It is almost touching. I think this way. It's a very small block. The dimension is something which we shouldn't ignore. But anyway, this is the reality. So as the block will fall down, the string will stretch and block will rise, the small block will rise. And now we have some angle relation. So first question is what is the constant relation? I'll just remove this part because this will confuse you. So what is the constant relation here? That's the first part. capital M and small m are connected by a single piece of string, isn't it? And the constraint simply says that along a single piece of string, the velocity component must be same, right? So V2 cos theta must be equals to V1. So the constraint here is V2 cos theta is V1. And that is the only guess you have to do. I mean, only hard work. The rest is easy. And now you have to think of dimension. This is 1 meter. And the base is like 2 meters. This is how much? Root 5 meter. But this length was 1 meter and now it has increased to root 5 meter. What is the ascent? Can you guess the ascent? Anyone? So what is the ascent of the small block while you hit?
Root 5 minus 1.
Correct. So this is okay, so many things. Now work energy theorem. I'll just write it, you can realize at home. Capital mg into 1 meter. I mean, I just write 1, not meter. It is okay. Do you realize this? The mg has gone down by only 1 meter. So no matter which path you choose, gravity work we only decide with the vertical motion, vertical displacement. So vertically, the block of mass m equals 2 kg has gone down by only 1 meter. And because the gravity is acting down, so it is positive work. What about the work done by gravity on the small mass? Okay. And the work equals to change in kinetic energy. So half capital M V2 square plus half small m V1 square. And let's put the value of m also. M is 2 kg. So 2g is 9.8. So 2g minus 0.5 into 5 minus 1 into g is 2v2 square. And here it is put to write as v1 is v2 cos theta. So it will come v2 square cos square theta. That's easy. And we can put the g value as, let's take 10 to just solve here. In the actual convention, it was 9.8, but you can take 10. So that's 20 minus 5 root 5 plus 5. Yeah. Is v2 square, this gets cancelled, plus v2 square by 4 into cos square. So cos theta is this. So cos theta is basically base upon hypotenuse. So this will become 4 upon root 3 minus 1 upon the square. So we can kind of do the anyway. So v2 square you can write as 1 plus root 5 minus plus 1 whole square upon root 5 plus 1 root 5 minus 1 is 5 minus 1 416. And this will become 25 minus 5 root 5. So very bad calculation for whatever reason, but this is the answer. So v2 square will be something and this will become 2.23 plus 1 whole square by 16. Okay, so this is how you have to solve, which you can do. But this is the question from JEE Advanced. Okay. Long time back. Imagine in 85, this was the level of question. Today, the level is not that difficult, but still it is difficult. So IIT has kind of not grown in difficulty, it has actually gone down in difficulty level. And now you have so many books to read, so many teachers to access the knowledge. Earlier it was not there, that's why okay, things were difficult at that time. So now these are the questions which are only based on the work and theorem. It also encompasses all the theory which you studied previously, like constant relation. Okay. And if you want to solve more of this kind of question, which one should, because you will get a lot of question in Aerodop of similar nature. In fact, there is one question which I would like to solve. Okay. Not particularly given here, but maybe. Yeah. 1.76. So 1.76 from Eurodot. Let me draw the diagram first. So this is kind of familiar to you. So this is the diagram, and question says that in the arrangement shown in figure, the mass of body 1 is eta times as great as that of the body 2. So the M2 is eta times, sorry, the mass, okay, ulta. So M1 is, and eta is given 4. M1, M2. All right. H is given 20 centimeter. Find the maximum height attained by M2 Okay. Assume system is released from rest. Okay, that's it. So you think about it, then I'll solve. Okay, don't solve this question. I'll solve. So think about the question. What is going to happen actually? Any guess? Just guess. No need to solve. I'll solve. Just guess what will happen. What you can say about this motion.
So basically M1 is going to descend and M2 is going to ascend.
Yeah, but M1 will descend only up to H height, right?
Yes.
And after that, it will hit the ground. And let's say after hitting the ground, it will come to rest or whatever. The question is, what will happen once M1 is hitting the ground? What will happen to M2?
M2 will be at its maximum height.
No. M2, the first of all, the moment M1 will hit the ground, the tension will become loose. M2 will try to move upward because of the velocity, right? And therefore the tension becomes zero, and therefore the motion afterwards will become free fall motion. So actually there are two types of motion here. One is called the motion due to the pulley block problem, which is like uniform motion. And then we have the free fall motion. So there are two parts in this question which you need to realize. It's not so easy. So the free fall motion will cease, sorry, the uniformly accelerated motion will cease for M1 after some time. And M2, because having the tendency to go up, the tension becomes loose, and therefore it will perform free fall motion up to the maximum height. So there are two parts. One is when M1 will hit the ground, what is the height of M2 at that instant? If M1 will descend by H, M2 will rise by? Any idea?
H.
No. That is a constraint.
2H.
2H. This is the first thing you need to realize, that if M1 will descend by H, it will go by 2H. So 2H is anyway you are there. And then at that instant, it will have some velocity which you need to actually calculate. So you can use the laws of motion to calculate, or work energy power to calculate. I'll do work energy power because that is what we are studying. So to get the V, see what I'm going to do. So, okay. Just before hitting, I mean, M1 will have velocity V1 and M2 will have velocity V2. And what is the relationship between V1 and V2? So similar to the ascent, because if M1 will go down with H, M2 will go up with 2H, it means velocity will have also the double value. So if I call this as V, this will be 2V. So I can write 2V, that's easy. So this is your constant part. Do you realize this part?
Yes, sir.
And now we can add the work energy theorem. So I can write, okay, work energy theorem. I'm writing here only, not two. So M1 GH, the loss, M2 G2H, the gravity is doing negative work. So net work done is this much equals to changing kinetic energy. So M1 into V square and half M2 into 2V whole square. That's very simple. You can see M1 is 4M2. So you can add 4M2 GH minus 2M2 GH. M1 is 4M2 V square plus 4M2 V square by 2. So M2 gets cancelled everywhere, right? That's the whole purpose. So this becomes 2GH and this side becomes yeah, 4/2, 4/2. It seems to be right. So this is how much? 4/2, 2 to the 4, correct? 4 V square. So V square turns out to be how much? GH by 2. But anyway, from here, because the motion beyond this point, because this rope will become slack, it will slack because of the continued motion of the M2, and it will happen the free fall. And we know the maximum height is how much? H max will be V square by 2G, right? This is how we study in vertical motion, which is 4 V square by 2G, which is like 2 by G into V square, which is GH by 2, which itself is H. Interesting. So the maximum height attained by the M2 is 3H. Therefore, maximum height attained by M2 equals to 2H because of the regular motion and H extra because of the free fall vertical motion. So 1.676, let's see the answer. What is the answer? Yeah, correct. So it is 0.6 meter. H is given how much? 20 centimeters. So
20.
60 centimeter, which is 0.6. And that is the right answer. I hope you realize this. I mean, I don't know, but you can spend some time thinking about this problem. So these are like some more challenging problems. You have to think a lot about situation. It's not easy to master at one go, but definitely with practice, you can master it in a better way. So now your homework is to solve SEO as much as you can. And the next lecture will bring some more forces into picture. Something more. Do you have lecture right now, Siddharth?
Yes, sir, at 9.
Okay, fine. So you can go for lecture. And we'll continue the same. This week, can we keep one extra lecture or maybe on Sunday?
Fine, sir.
All right. So